I think, your Lean Pub page that Haskell has not quite grown up yet. It's in its mid-30s and it wants to be Agda when it grows up. So is Haskell...
Did I say that? Oops.
You wrote it and put it on the internet.
Oh my goodness.
So is Haskell going to grow up? And if so, when? And what kind of adult will it become? And will it be as much fun to play with when it's an adult?
I love that. Yeah, I think Haskell is a fantastic language, and I think maybe what I meant more by that was dependent types are fantastic. And in Haskell, we have all of these language extensions, which sort of the confluence of them allows us to express dependent types sort of in this weird, hacky way that's after the fact. And it can get the job done, but it's not ever pleasant to do. And I don't know about you, but my experience with weird sort of arcana like this is you learn all the features one by one. That is to say, the Haskell language extensions, and over time you sort of get the gestalt of what they're capable of doing. But it's all very ad hoc, and so when you go to a language like Agda that has dependent types built in, it's a breath of fresh air, where all of a sudden you're not fighting with the compiler to express ideas. They're just functional programming. You're just doing the same programming on types that you were at the value level, and it's an extremely natural sort of next step. So I found most of my complaints about Haskell are really sort of unfair in many ways, which is they didn't know these things when they got started, right? And so Agda came along 20 years after the fact, or however long, and said, look at all the things we can do, and all of these features that happen to be the same idea. So will Haskell ever get there? I'm not sure. It seems like too big of a breaking change to me that we'll ever really get truly dependent types. That being said, I follow the GHC updates, and it seems like I'm wrong about that, because every release they're pushing visible types, and I'm hoping to be wrong on this, and I'd love to see it. I don't know if that answers your question.
It's that I was starting to sort of ask you about correct by construction, but maybe I should flip over to thinking in types. That's was your first book, and was that the motivation behind that to bring those ideas together, or like?
The motivation for that one was just I had spent enough time sort of feeling the pain of learning all these language features, and thought I should probably just write it down. I had recently quit my job and moved to Lithuania, and was trying to speak Lithuanian, but it was doing a very poor job of that. And so because of that, I didn't have a huge amount of friends, just because I wasn't able to articulate myself, and I was sort of stubbornly insisting on trying. So yeah, I think really that was just me looking for a project to get out of the door, and to, yeah, so that's sort of where it came from. I think it's had quite a lot of resounding success, though, in the ecosystem, and I think it sort of accidentally preys on the weird imposter syndrome that so many Haskellers have, myself included. Which is to say, like, I think everyone's sort of aware that these things are here, but it's never entirely clear how you get there.
Yep.
I just got completely lucky, and this thing I wanted to write about happened to be a thing that there was a lot of thirst to learn.
And if you are wrong and they bring dependent types fully into Haskell, is there going to be a thinking in new types, or
The fantastic title. I actually was looking at putting together a second edition of the book, because I think I published it, and like a month later, Chongar Kiss put out a blog post about parsing strings at the type level or something quite remarkable, which immediately made my book sort of obsolete in some sense. So there was a new technique that wasn't in the book, and that happened like a week or something after I published it. So I've always been kind of annoyed at him for being as brilliant as he is. And so there is sort of a second edition in mind. I always like to go back, and the book itself is quite theoretical and says, here are some things that you can do, and often doesn't provide the wisdom or the experience of like, when should I use these things? How do I use these things in like earnest? And how do I actually solve problems with these things rather than just look what I can do? So I've always thought there's quite a lot of room there for like what I'm calling like war stories, which I stole from the algorithm design manual by Skyna, which is he talks about an algorithm, and this is like, here is how this actually played out in the real world, where I had a real problem and we tried something that didn't work, and so I put on my algorithm design hat and we came up with a better solution. So I would love to discuss problems in past companies or things where we found a gnarly bug, and being able to exploit behavior at the type level let us eliminate classes of bugs that were harmful and in a few cases extremely expensive.
Very cool. Looking forward to that one then.
Yeah, cheers. It hasn't really actually, sorry, that's there are some quite new features in the language itself, like linear Haskell and predicative types, and there's a few other things that I've sat down and wanted to write about. But the last time I looked at them, which was probably 2 years ago, these features were clearly not ready for prime time. So I sat down for a week and like went through the papers and said, can I implement anything with it? And the papers turned out to be not what was implemented, and so the examples in the paper didn't work in the modern version of Haskell. And so it seemed to me like I could write this book, but there would be glaring holes if I didn't cover those things. But also, if I were to cover those things, it was clearly not. I didn't have much I could say about them because they didn't seem to be fully fledged. So I think that's sort of what killed the project.
So yeah, could be just a matter of time until.
Yeah, I would like to revisit it at some point. I think probably the lift to thrust ratio. I don't know if that's relevant here. It's late, but I think that was a huge amount of effort on my part, and I think the results would definitely be worth it. Just a question for you, John. I noticed there's chat going on. There are questions for me. I don't know if you want to field those or if I should just jump in and.
Phil, what we were planning to do was to have a couple of question monitors to jump in, because I've got some of the same questions probably in the background, but feel free just to, when something comes up that I'm happy to skip over a question that someone's beaten me to the punch to, so feel free to pick it up and run with it if you like.
Cool. Ben asked just if I ever got over my hump of learning Lithuanian, and I did, but that was because I left the country. So I never actually got never got anywhere with it.
Cool. Okay, I might just cycle back to the latest and greatest, the certainty by construction. So can you just tell us a little bit about certainty by construction, what the motivation was behind that one?
Yeah, I have a weird set of friends in real life, and we're all sort of unemployed or underemployed at least, and all interested in mathematics and have way too much time on our hands, and also this like weird desire to like find some deep truth in the universe. And so I have some friends who came to me one day and they said, we want to combine quantum field theory with like game theory or something, and so we want to figure out what happens when you put John Nash but like in superposition or something. Didn't really make a huge amount of sense to me, but I was learning Agda at the time just sort of on a whim, and I figured I would just sit down with them and see if I could be of any use. I had no idea what the domain was. I don't know anything about quantum mechanics or game theory, but it turned out I was like significantly more helpful to the effort than any of us were expecting, because I sort of insisted that we write it down in Agda and like really try to formalize what it is we were trying to say. And I think it's really easy when you're doing math to accidentally fool yourself in understanding what's going on, because as programmers, so much of at least how I operate is I will do some work and ask the compiler, and then the compiler is this instant feedback that says, did you do it right or not? And in mathematics, that doesn't seem to exist, right? In mathematics, you sort of hopefully have a professor or a mentor or something, and your feedback is you ask them, does it look reasonable? And if it comes back without too much feedback, then you're probably fine. And so the point being, it took me a long time, for example, like understand really what a homomorphism was, because when you look at it syntactically, which is the only way it can be presented in the book, it looks obvious. But when you experience it in the real world, the syntax collapses and the computation happens immediately. And so you don't see the obvious syntax. And so the point being, I was convinced that I understood this material and I had no idea what I was talking about. And catching yourself doing that a few times is quite a humbling experience. So all of this was to say, I was finding Agda really useful as a tool for thought in sort of tackling domains I didn't know too much about. And it seemed like a natural progression in my functional programming journey to sit down and figure it out. So one thing led to the next, and I had more time on my hands than I perhaps should have. And writing, and it was a great excuse for me to learn a bunch of mathematics that I'd skipped over, and doing them to a point where the computer will accept your proof really, really helps drive these things home.
Right, very cool. So I've just started working through correct by construction. I made the mistake of reading your first two books, and yeah, I'm not going to do that again. I'm going to actually work through it this time. And yeah, chapter 1, it still feels fairly Haskell-y and fairly familiar.
Yep.
What point do you think I'll get to where it really kicks me in the guts that this isn't Haskell anymore? This is something different.
Chapter probably 3 is probably where things kick in. Chapter 1 is the vibes, and chapter 2 is like, what can you do in Agda? I think maybe it's the other way around. But all of a sudden, find the natural numbers for yourself.
Mm-hmm.
I didn't do a math degree or anything, but I sort of was familiar with piano or arithmetic just by like the nature of needing to do numbers at the type level in Haskell. So like these things were sort of in the folklore or maybe in the zeitgeist for me. But being able to like define addition for myself, that was kind of interesting. And then proving that addition is associative, right? Which is to say that it doesn't matter where you put your parentheses, that you get the same answer all the way. Like I had no idea what proving such a thing would mean. Like what could that possibly look like? What does it mean? It just sort of seems to be true.
Mm-hmm.
I think, yeah, by the time you sort of start talking about equality types, which allow you to articulate that these two values must always be equal. So you have a type that articulates the fact that two values are equal at all times. That's a thing that just cannot be expressed in Haskell. And so as soon as it changes your language from being this sort of like implementation only language to a language in which you can actually prove things about your programs, as say not like with tests or not stochastically or not sort of best effort, but the compiler will verify that every step of your reasoning is true, and therefore that your conclusion must be true as well.
Cool. Yeah. So do you think your audience for this book, you think
surprisingly small, it turns out.
Hey?
It's a surprisingly small audience.
Really? It's
Yeah.
you're number 8 on LeanPub. Um, so, you think this will appeal to like working developers, or you'll have to be into Haskell and FP first and be on that journey on the way, or?
I don't know the answer to that one. I think there is, in the same way that sort of Haskellers had this imposter syndrome around type level stuff. I think a lot of programmers have this sort of imposter syndrome around mathematics.
Yeah.
And I think for me, a lot of the appeal of Agda was I could leverage my programming skill in order to learn this topic that I wanted to learn.
Mm-hmm.
So I think there is a possibility that this would appeal to average programmers, or maybe like everyday programmers, the ones who are not deep into this FP stuff.
Yeah.
But I think the inferential distance is probably too far. In that, like, if you were to come at this just being a Java person, not only do you have to tackle the math, but you also have to tackle the syntax. You have to tackle the idea of like purity and not having variables, and there's a huge amount of mental load that you need to tackle that I think would unfortunately divert from the message.
Mm-hmm. Mm-hmm.
Yeah.
Yeah. Cool. So is that you mentioned something called the well, can't pronounce it now, co-blurb paradox in your intro.
Yeah.
Can you tell us a little bit about the co-blurb paradox, and also when's it going to hit me as a part-time Haskell working through your book? Yeah.
Cool. So the context here is Paul Graham wrote an essay. I don't know, beating the averages, I think it's called. He talks about the blub paradox, which is it's sort of easy to look down on programming languages. If you have a programming language in mind, you can see languages that are less powerful because you can compare them against the features you know about. And if those features aren't there, you can say, Java doesn't even have hard kind of types. Therefore, how could I possibly how could I possibly program this thing I want to program? Therefore, Java is awful, right? Which it is, but not necessarily for that reason. So that's sort of the blub paradox, and he talks a lot about that, which is sort of you can always see the languages that are weaker than you, but it's harder to spot which languages are better. His argument is that Lisp is the one true language, and it's and that's sort of why he was able to succeed. In writing a lot of Agda, and I guess doing Haskell professionally, often with a lot of like junior programmers, I've sort of seen the corollary of this, which I call the co-blub paradox, which is that if you know a weaker language, you're often having to do this like fancy footwork in order to work around problems in the language. And because those problems are invisible to you, then it's unclear when you're doing this. And usually that fancy footwork you're doing is not only unnecessary, but it's often actively harmful in a language that doesn't require it. So I have an example that actually I've been thinking about quite a lot recently, which is graphs. And in a language that doesn't have particularly good typing capabilities, you can sort of express any data structure as a graph, right? In the same way you can express any value as a string. If you like try really hard to throw away all the things you know about it, like these structures are so flexible that you can express anything you want as them, but at the cost of you have to reparse all the things you know out of it again. And so in a world, sorry?
Sort of like JavaScript and JSON sort of.
Yeah, exactly. Right. Which is like JSON doesn't have, JavaScript doesn't have sum types, right? So you can't do tagged unions unless you tag it yourself. Mm-hmm. And because of that, you have to tag everything yourself, and you don't even realize there is this thing missing. And so then you can take that and you can go to Haskell where you do have sum types. And instead of using a sum type, you might use a record where you have a Boolean and then another two fields, and you sort of fill in one with like an error value if you were to access it and the Boolean is the wrong state. So it's sort of stuff like that, right? Where you don't have a feature that you're looking for a feature and you don't realize you're looking for it and you don't realize that you don't have it. And so being clever, ingenuous people, right? We figure it out and we make something that works, but it's usually to the detriment of our programs if we knew exactly what it was we were looking for.
Sort of, I think when I started learning Haskell, the first thing I looked for was how to do a loop and how to mutate a variable.
Right. Great. Yes.
I thought, what is this pile of crap language? I can't even do a loop, you know? So,
yeah, exactly. Right. Like I want to just log something. Why can't I just talk to the network here? Right. And it turns out there's really good reasons for doing that, but you don't have the experience or the context to even realize why these constraints are there, or yeah.
So when you were you mentioned in your introduction to to certainty by construction that you bounced around between proof assistance for about a year before you settled on Agda. So what was it about Agda that led you to choose Agda and not this be a book more about Lean or Coq or something else?
Well, I did actually try Lean for a while. I found some online game where you sort of write some Lean and you prove things about the numbers. Turns out proving things about the numbers is a rite of passage, and regardless of the context or the book or the language. But I got all the way through this game on Lean, so I was proving like the commutativity of multiplication, or that multiplication distributes over addition, or something like non-trivial facts about natural numbers. But in Lean, you have sort of these two separate languages where you've got like the pure language, and then you have this new this apart tactic language where you're sort of manipulating this invisible state, which corresponds to like the goals that you haven't solved yet, and like essentially it's a language that writes code for you, but it doesn't look like the language that you have. So I made it all the way through this game in Lean, and I was able to prove things, and I had no idea what the hell was going on. Right, I was able to prove the thing, but like I didn't know why my proof worked, or if you were to strip away the syntactic sugar, what was actually happening underneath the hood. I think the other thing that actually bounced me off Lean was I was trying to formalize my like first year mathematics course from university in it, and I got stuck trying to prove that the cube of the cube root of a number is equal to the number itself. And that was not that took like multiple months of the entire Lean community, it seemed, to like try and solve this. And I think it just happened to fall between the cracks of what they had proved. But it was challenging and sort of frustrating in the sense of it seemed like an obvious lemma that should exist, and yet none of us could get it. So I sort of just hit a wall pretty early. My feeling is that Lean is sort of the proof assistant for like C++ programmers, and Agda is the proof assistant for Haskell programmers, in the sense of like these languages feel like they have evolved from that. Like a C++ programmer going to Lean is not going to be too surprised by the syntax or the semantics, sort of similarly from Haskell to Agda. And so I think the fact that I ended up on Agda was more just that I happened to be a Haskell person more so than anything. Which I think answers Ben's question here about studying Lean. So I don't think there's anything particularly unique about Agda. I might be wrong about that, but I haven't really explored the field. As for Coq seems insane. Just it seems like it's got the worst syntax in the universe, and I think the only reason it continues to exist is that there seems that like it got its claws in early. in that it's just there's I think it's software foundations or something, some high profile book about Coq that happened early, and I think that's why it continues to be used. I apologize for all the people I just offended.
So was certainty by construction a progression from algebra-driven design? Your second book.
I think yes and no. In retrospect, algebra-driven design was really a manual on the lost art of combinator library development. I didn't know that at the time when I was writing it, and I sort of only pieced that together after the fact by talking to Mike Sperber. But it was more, given a problem, how do you sort of decompose it into reusable pieces and then prove that those pieces are what you want and that they sort of cover the space of problems you want to be able to articulate. Excuse me. And then, so there was sort of that half, and then there's the second half of like, how do you make that palatable for Haskell programmers? And that comes with a lot of like automated tooling and sort of things like quick check and quick spec. And I think that stuff is much weaker in the book than the how do you design combinator libraries part. So, so certainty by construction, I think, does indeed follow, but only from the second half, which is the how do you make this sort of palatable, or how do you work towards proof. So a lot of the theme of algebra-driven design is sort of writing property tests and generating property tests and trying your very best to get a high degree of certainty that your code does in fact work and does what you want. But we do that stochastically, and we try to make it as easy as possible to just generate 1 million tests. And if 1 million tests pass, you're probably fine, right? But certainty by construction takes it the next step and says, let's not do this stochastically, let's just actually prove this thing.
So when you first announced algebra-driven design, it was under the heading Design and Interpretation of Haskell Programs. So does the name change reflect some sort of insight you gained throughout writing the book, or was it something that happened later? Or
John, I'll admit a fact to you, which is that writing a book is a miserable experience.
You've done it 3 times.
I know, because I'm an idiot. It's really fun for the first week when you have like a bunch of ideas and you start putting them down, and often those ideas do not work as well as you thought in your head, and they don't usually mesh particularly well. And so I think design and interpretation of Haskell programs was originally going to be about sort of free monads and sort of a stylistic, like how do you write good Haskell code sort of thing. I don't know if I really had a plan for it, but at the time I was really thinking about free monads and polysemy and that sort of thing. And it seemed like the future of programming, which I don't agree with anymore, but it seemed at the time like we should sort of work syntactically and reinterpret these programs however we choose after the fact. So I think the eventual book ended up being nothing like what it was, and that one just didn't happen to stick.
Right.
Yeah.
And part of it not sticking was like there's like 2 tangents in your answer that I'd like to go off on. So I'm gonna go off on one tangent and then try and come back.
Sure.
So if it turns out a bit like Pulp Fiction, just apologies. So yeah, you mentioned freer effects and polysemy, and I think for a long time you'll be recognised as the creator of polysemy in the
Oh man,
Haskell community.
I don't know how I live that off.
Henry Winkler and Fonzie sort of situation going on there.
Exactly. Yeah.
So can you tell us a little bit about polysemy and your polysemy journey in creating it?
Cool. Yeah, sure. John, I just want to appreciate that you pronounce polysemy the same way I do. And most people seem to have this mouthful of polysemy, which I get, but doesn't it's never jived well with me. So, so the idea was, I was working at a software company just before I gave up working for the man, as one would expect. And we had this really awful nest of IO spaghetti. We were essentially writing C code, but it was in a Haskell compiler, and we didn't think we were, but like it just evolved that way. So everything was in IO, and just it was a nightmare to maintain. It was a nightmare to test, and because of that, we didn't really test it. And so we that worked for a few years, and then we accidentally sent out $5 million worth of coupons or something that we didn't have the money to pay, something like that, like something really, really bad for the company as a small startup. So that one hit us pretty hard. And so all of a sudden, there was a push for how do we test this, right? Like, oh, testing is important. It turns out, who knew? So I got tasked with a few other engineers of what could we have done and how do we get there and what could testing look like. And one of my colleagues, Nick Childers, he was really big into the Scala scene where they have a free monad library. I think it's called Freak or Freak-K maybe. So the idea of a free monad is sort of monadic monads allow us to separate the computation from the description of the computation. And so you write the program and you describe the effects you want to happen, but you don't necessarily need to do those effects. And that gives the runtime some more decision about when these things happen, or it gives you some composability saying, I want to build this action and then run it multiple times. And I can do that if I separate the description of it from the interpretation of it. So that's sort of monads in general. Free monads take that a little further. Oh, sorry. Oh, okay. So free monads take that a little further, which is say, I'm going to have some primitives in this language, and I'm not going to give them any meaning at all. And so what that means is I can now sort of program against this completely abstract interface, and after the fact, figure out what all of it means. So in Haskell, this means you're not just working in IO, you're working in a monad of your own devising where you have a data type that corresponds to talking to the file system. And so rather than ever actually talking to the file system, I use a constructor that says if I were to talk to the type system, I would want to do this to the type system. And so there is something kind of nice about this, at least in theory, which is you can write your program and you have an intended semantics of these things. And then in production, you run it against the intended semantics in IO, which is say you interpret all these abstract symbols as IO actions. But in testing, you don't need to do that. You could perhaps, you can do mocking sort of very easily because there's nothing to mock. You just interpret the same symbols differently. So this seemed like a really cool idea, and we played around at this company with what happens if we took this idea really far and built the entire thing out of it. And we built a few components completely out of free monads, and it was actually quite a joy. The components themselves were pull data from somewhere, decrypt it, send it somewhere else. So they were super simple things, but the experience of writing it was really, really delightful. And so I got quite excited about this effect, or no pun intended. And I just got really excited about the technique, and I ended up leaving the country the company and then the country, and just had this idea of free monads seemed like a really cool solution. I didn't really have an idea of what exactly the problem was, but I spent a good chunk of the next couple of years sort of hashing out that idea and seeing how far it can go. Turns out I don't think it goes particularly far. and the problem is we actually don't want to work at the level of syntax. Syntax is the wrong level. Because at syntax, when you work with syntax, you don't really know what the semantics are. And you have an intended semantics in your head, but nothing forces the interpretation of that syntax to correspond at all to the semantics. And so I guess in my more modern parlance, I'd say like there are laws we'd expect to hold that do not when you're operating at the level of syntax. Both that means the interpretation could do something wrong, which is they could break those semantics, or I could accidentally branch on the syntax itself, which is say branch on something that doesn't exist in the actual semantics. Right, you can sort of imagine working on mathematics, and you can say like, if my variable is x, is like the symbol x, then I'm going to do something. Mm-hmm. Which, if you're not careful, it's a sort of easy mistake to make. And what really prevents that is thinking only and being able to only talk about semantics rather than the syntax.
Hmm. So, faced with the same problem today, what sort of strategies would you use to clean up your $5 million coupon issue?
Yeah, I think I don't really have a great solution. The best solution I have is like really embrace functional programming, right? Like we were writing Haskell, but it wasn't really Haskell in like the sense of if we were to write it again and had like more senior people, I think, tackling the problems, the code base would look extremely different and it would have been much easier to test. And I think this is a thing I'm actually currently experiencing at work, where you have code that turns out to be legacy code just by virtue of you coming onto the project late. And it's much more expensive to fix it after the fact than it would be to write it sort of properly the first time around. Which is say like, keep the pure and the impure stuff as separate as possible. Use types judiciously, think about the types, and sort of don't paint yourself into corners, right? And I don't think any of those are magic bullets, but they go a long way when you're actively doing all of those things.
Mm-hmm.
Yeah, so I don't know if that really solves the problem necessarily, but it sure helps a lot.
Cool. So going off on my other tangent, you mentioned that when you're talking about algebra-driven design, that you write 2 books for every book that you produce or more. It's pretty tough. But jumping back even further, you announced you're starting certainty by construction in. When did you start it? In mid-May 2023, and you were done by late October. So how did you pull that off? Was it just sitting in your brain ready to jump out, or
I had already written 1.5 books by that point.
Right.
By the time the actual idea had gelled, it was clear that the book was going to be me figuring out mathematics and using that as a springboard for showing off Agda, and more generally, how do you prove things about software? And in that time, I had written a huge amount of material, some of which made it, some of which didn't. But I think the other thing is when you're toiling away on something that nobody knows about, it's it's really hard to ever ship it.
Mhm.
And so for me, often announcing a project is the forcing function that gets it out the door. Where I had been working on this thing for over a year at that point. Is that true? I don't know. Maybe around then, half a year. And there was no end in sight. And at some point, you sort of just need to say, I'm doing this, and come hell or high water, I'm committing to it and I'm going to make it happen. And for me, that is a huge source of neuroses, but also a huge source of actually getting things done.
Mhm. And when you finish, do you collapse in a heap for 3 months and lie on a beach? And
Oh, I wish. You just certainly collapse in a heap. I write a personal blog alongside the all the programming stuff, and for 10 years now, I've had a tradition of sort of writing a recap of my last year, of all the things I learned and what happened. And it's now end of March. I'm still don't have it in me to go and finish that off because I'm just so burnt out on writing right now. So yeah. Yeah, at the same time, I actually finished it while I was in grad school. I started grad school for one semester, turned out, in September, and so released the book in the middle of that, and therefore didn't really have the flexibility or the opportunity to take any time off after it, which was kind of okay because I spent 5 or 6 years taking time off.
right.
Yeah.
And when you are in the in the middle of a book or one of these projects, what's your process like? Like, is it just mad 12-hour days madness, or is it all balanced out and scheduled? And
No, I'm completely haphazard. My only rule is you work on a project every day, because if you work on it every day, it can't die. And so some days that means it's 11:30 p.m. and I'm in bed and I realize, oh fuck, I didn't make a commit today, and so I'll go and I'll change one word just to keep the streak going, right?
Yeah.
And that's okay. That's completely in the rules. But it's really and truly don't stop on it, because as soon as you don't work on it for a week, it's really easy to go another week, and then this thing I've spent 6 months on all of a sudden just dies in the water. Besides that, usually it's this combination, or sort of this wave between having a really good idea and being really inspired, and you go and you write it down and you spend a huge amount of time proving things, only to get to the very end and you say, I haven't set this up properly, or this proof was much harder than I needed and I need to sort of back up and prove something first. So the order is not nearly start at the beginning and get to the end. It's this weird back and forth where you'll work all the way up to chapter 6, and then you realize, I haven't explained some concept because I didn't know it existed. And so then you have to go and research that and then figure it out, and then you have to insert it into the right place in the book, which adjusts everything else before and after it. And so sort of keeping everything together is, I'd say, probably more than half the work, is just the continual making it cohesive and continuous. And I don't even think I'm particularly good at that. And nevertheless, that's still most of the work, I'd say. So a few of those chapters I think got written 6 or 7 times. And each time they get better, right? But you sure get tired of writing about setoids or something.
But it comes through in the writing. I find your books are really very personal, in the tone, like something very technical, but it's coming off in a very accessible and way, or the way you write. So it's really, you can tell that you've put a lot of effort into polishing it. It's it's pretty amazing.
Thank you.
Yeah.
Yeah. I guess on the more technical side of the writing process, I wrote my very first book in LaTeX directly, and that felt like a good idea because you can immediately get something that looks pretty. And that was fine until I published it and wanted to make an EPUB, right? So like an ebook version, and that ebooks turned out to be like this horrible mishmash of HTML and like CSS from 1998. And there is, as far as I can tell, no ebook backend for LaTeX because it doesn't make sense, because LaTeX is about presentation and ebooks are about or HTML is more about the semantic notion of here's what these things mean, but I don't have any notion of presentation. So that turned out to be like a nightmare experience to try and get an ebook version of that. And it turned out to be like this 500-line bash script that would like sed and awk its way through the LaTeX, trying to turn it into something that resembles HTML. And it like kind of worked, but it's fucking awful. So that actually taught me quite a lot about, it's sort of the same lesson I learned in programming, right? Which is you want to sort of separate your concerns and again, work semantically, not syntactically. Where, so my last two books have been written in Markdown.
Mm-hmm.
And that gives you a nice semantic layer to say, like, here's the content. And I pushed that through Pandoc, which is a fantastic Haskell library for manipulating documents. And in particular, Pandoc has the notion of like extensibility through filters. And so you can write Haskell programs that connect to the library and then can manipulate the document however you choose. So that turns this, like the presentation of the book, into a programming problem, where now I sort of need to add some annotations to the book itself, but I can process those after the fact. And so it's a lot like LaTeX macros, in the sense that I can sort of make a new function or something that articulates something, but having it be through a separate path rather than LaTeX allowed me to sort of make all these things happen. Paul asks, what software do I do the writing in? I do it in Vim. Yeah. Do I keep an ideas database? No, but I do use a program called Workflowy, which is like just nested bullet points. It's fantastic. Workflowy.com. I recommend that. But it's super low key and low energy and boring. I also just keep a lot of like markdown files around where I'll like I'll flesh out the ideas by like heading, and then I'll just put those into the book. And then the next time I come around, now I've got some structure to write into. So get a lot of value out of that as well.
Cool. I'd like to just ask another few questions about
Sure.
algebra-driven design. The way you've structured it is quite interesting. I was wondering whether that's came in the terms of having the two algebras and then the two solutions following that in two sections. Was that what was the motivation behind that, and was that something you came up with at the start, or is it something, one of the refactoring rounds you went through that got you there?
That was definitely one of the refactoring rounds. I feel like most of my books are me trying to teach myself something, and in this case, it was sort of trying to figure out how do you operate on combinators. But there's sort of the didactic side of things, which is how do you keep a reader engaged and how do you get them to ponder the questions you want to ponder? And that's a really hard problem. So I sort of figured if you present the problem and then the solution and then the problem and then the solution, by the time you're on the second iteration of thinking about the problem, you forgot how to do it, because you had all this other stuff that happened in the meantime. And so to me, that was sort of the more valuable skill. And I was I think I had 2 or maybe 3 more examples in the book as originally, but it got unwieldy long, and so I chopped them out, which I think was a disservice to the book. But done is better than perfect. So, but yeah, I would have loved like 3 examples to really hammer it home, saying here's the technique. Think about it. Let's try it. Okay, here's a new one. Now you've got the tools. Maybe you can think about it yourself before reading on. But I think you lose that when you've gone through the entire processing and start again from scratch, at least on your first time through. And I'm sort of flattered if anybody reads it once, let alone multiple times. So I wasn't really expecting that to happen.
To me, that design, like reading through your first chapter, there's a suspicion in the back of my head that it's come from an academic paper, and the problems being picked to match very closely to the technique. So it's kind of like, yeah, I'm not convinced of this. But then the second example being the scavenger hunt kind of allayed those concerns, and it also kind of invites working through the book twice, like once end to end, and then going back and hopping from working through and hopping from the algebra to the implementation on each, and that's certainly something I'm planning to do. But yeah, thought that was really cool.
I'm delighted to hear that.
So it's called algebra-driven design. What's the relationship between algebra-driven design and denotational design?
It's this thing I've been trying to work out. This is Connell Elliott's notion of denotational design, I imagine. Yeah, it's I've been trying hard for many years to figure out exactly what Connell means by denotational design, and I haven't been super successful with that. But I sort of feel like there's this iceberg that I've got my pickaxe, and I'm slowly chipping away at the problem. So my understanding of denotational design is more we should think in terms of denotational semantics, which is to say you sort of forget all the clever implementation things. You forget about computability. You say, if I were to model this thing mathematically and as simply as possible, how would I go about doing that? And if you once you do that, you sort of get a good model of the problem, which you can sort of use as a reference for anything clever you might do after the fact. So anything clever you do has to correspond with the denotational semantics. And what it means to be correct is defined in terms of the denotational semantics. So I think that's the part I have managed to chip off from Connell. I think I think there's more that he means when he talks about this, but I haven't really managed to make too much progress on that yet. So how does this correspond with algebra-driven design? Frankly, I just thought it was actually a cool title. And it is about algebras, but so I guess the distinction is algebra-driven design. You're saying here, I'm going to just make up an algebra, right? I'm going to just say like these things I expect to hold. And I'm not too worried about the denotational semantics because I'm not really trying to model it. It's been a little while since I've read this book, so I don't know if this actually corresponds to reality of what the book is. But there's a lot more emphasis on sort of modeling the features of the domain, and then saying, here's how these features should relate to each other, rather than trying to say, what is the domain? Right, so I'm modeling more the surface of the domain rather than trying to say, what does it mean to be in this domain? So when I first heard Connell talk about denotational design, I was working at Google and their access management platform. 'And So I thought I was currently in the middle of like a big redesign for how does Google do access management, and it seemed like a good opportunity to tackle the problem. And so we were doing access management, so we had like the notion of users who could belong to groups, and those groups could have roles associated with them, and those roles could have permissions on resources. And so we had like all these different things of and so if you were to sort of do the algorithm design thing, you'd say, well, I have a user, and that user can be modeled as like being in this group. And you can sort of express the relationships between those things. But when you think about it denotationally, all of this reduces to a function from a user to a permission to a resource to Booleans. It's like, is this person allowed to do this thing? Right? Like that is what you're trying to model. And the rest of it is just sort of cruft or computational like chipping away, or like none of it is really important to the problem domain. It just happens to be where we landed. So I think maybe that's the best I can sort of do to articulate the difference. Yeah, I do think the denotational semantics are huge, especially when you're working in a domain where it's less clear what correctness means. It's less clear when you have the right answer. And so the algebraic approach is useful when someone says, here's a thing, make it better. And the denotational approach is, I think, more useful when you have a greenfield project and you want to say, what should this look like? In an ideal world, like, how do we make this the best thing it could be?
Have you ever had beers with Connell Elliott?
I have never had beers with Connell Elliott. No, I would like to. We've chatted a little bit online, but I've never met him in person.
So since since you first started writing algebra-driven design and correct by construction, have you got much feedback from the world about these ideas? Like, are you seeing any sort of shift towards sort of a more rigorous approach to things, or you think it's just business as usual in the big bad world? And
I wish I could say that things are changing. I don't think they are. But maybe on a personal level, I have noticed things where I'll occasionally meet someone, and for whatever reason, the book really spoke to them. And so one person described algebra-driven design as like changing his life, which seems like hyperbole to me, but extremely flattering, right? And so I think a lot of it is sort of worth doing, even just for little stories like that, right? I feel like there's a second part to your question, but
yeah, well, that was generally it. I guess follow up to that, and that's why is the world like it is? It's like I read your books and and see other sort of techniques that just seem so much better than what the zeitgeist is. And the Darwinist in me thinks that over time the people who choose these techniques will prevail, and the people who shift things on Kanban boards and hire a new manager every time there's a problem will wither and die. But doesn't seem to be the case. Would you sort of agree with that in any way? And if so,
I agree on like the reptile brain level. But I try to keep it in check when I remember it took the world like 40 years to embrace automatic memory management. Right, like that idea was around for a long time before it made any progress in the world. And then you think about lambdas, which were invented before computers, and Java got them in the last 5 years or something, right? and so if on that time span, like if I don't think it's going to happen anytime soon, but I do genuinely think we're making strides in the long run, and we will, in the sense of software is getting so big and so important that it's often really painful when you have these bugs, right? So I'm not particularly big on like crypto stuff, but what I do see kind of quite cool coming out of the crypto stuff is because these people are dealing with a huge amount of money potentially, they're much more adverse to bugs. And so I think it's IOHK or IO Global, I guess they're called now. They have like an Agda team, and they're like hiring proof engineers for the thing they're doing. And I think that's a really promising sign, right? Where there are some domains where failure is so expensive that it's worth paying to do things right. And I think that's sort of fundamentally the tension, right? Which is a lot of software doesn't need to be right. And
Right.
we're all here because we like doing things the right way, and that's why we're in the Haskell user group, right? But most of the world doesn't feel that way, and I think we usually do it because it feels good and not because we have a particularly good business reason for it. So, like my phone doesn't fucking work ever. None of the software on my phone works, and that's kind of okay because none of it really matters, right? Like if the top bar jiggles up and down, it's a little annoying, and it's kind of embarrassing that a giant company can't manage to solve that. But like, is it worth getting rid of their 40,000 engineers, or like training them to do something different? Probably not. So I think the status quo works well enough for most things, but you compare it to like the software we sent to the moon, or on Voyager, right, where allegedly every line of that was triple checked, or I don't know, they got a room together and everybody in the room like read through it together. Like code review was huge, right? And so I think that it's probably always been the case for the really important stuff. Like we do care, and it's more of a reflection of the software we're writing today that a lot of it isn't important enough to do well.
So what do you think AI, what do you think the effects of AI would be on the landscape?
I'm not very bullish on AI. I think I've actually seen this already with my junior colleagues who already have Copilot turned on at all times, and it writes code for them. But I think often they don't have the experience or the wisdom to know when it's doing good things or bad things. That's a little worrisome to me, which I would like it very much more if we had a sort of more reliable sense of uncertainty with these things, where if you're a junior programmer and you're not entirely sure what you're doing, it'd be nice to get more feedback from that in the code review rather than like a program that looks like it works. Right? Because if it clearly doesn't work, then I'm going to give it more attention. But if it looks plausibly right, I'll probably stamp it more likely, right? So my concern is that these things are going to leak in more bugs. I think that's not an insurmountable challenge. I guess I fall more into the AI doom side of things, and so I feel like by the time this is no longer a problem, we're going to have much bigger problems from AI. So in the short term, I'm kind of annoyed about it, and in the longer term, I'm terrified. But yeah, I don't see a particularly happy path for AI, unfortunately. Yeah. Kartik, I just got an email that someone bought Certainty by Construction, so thank you. Marvelous chips.
Which book should I read first? That's a really good question.
Depends on what you're looking for. They're all completely different. So if you're already a pretty good Haskell programmer and you want to learn some more, Thinking with Types is probably the most immediately practical book, in the sense of it scratches an itch you're probably aware of having. Algebra-driven design, I think, is maybe the most like longer term useful, in the sense of, I think it'll give you a new way of thinking about software that is quite applicable outside of functional programming and outside of Haskell, certainly. And then Certainty by Construction, I think, is just quite a lot of fun, but I'm not sure it has a huge amount of takeaway other than the industry sucks and we could do much better. But so maybe that'll be a little more frustrating to read. But that one's the prettiest. So I mean, it really depends on what you're looking for. But I guess the real answer is you should probably read all of them, and maybe buy the full set for everyone you know as well.
Can we talk a little bit about Wingman? I watched your Zurich Hack 21 demo, and that was pretty mind-blowing, and I also was pretty blown away when Wingman jumped in when I was using HLS and case split for me. So can you tell us a bit about tactics programming, the development of Wingman, and the sort of maintenance challenges that followed?
Sure.
Escaped into HLS. Yeah.
So the story starts with my friend Reed Melanix, who goes by Tot Woof online, which is not the most pronounceable name. But he's the guy who sort of got me into Lean and then subsequently into Agda. And I'd say most of the things I know I've sort of learned indirectly or directly through Reed. But he was working in Proof Assistance, and he had written this really cool monad in Haskell that would do sort of tactic substitution. And so tactics are this idea that you can sort of synthesize some piece of data and it's going to have holes in it, and then you can subsequently synthesize something in those holes, perhaps producing more holes. So you have this problem of I want to turn one hole into some amount of syntax plus some more holes, and then once I filled all the holes, I want to reconstruct this thing back into some data type. So the way I think about this, maybe the most obvious thing is when you're writing code in Haskell and you're using typed holes, right? So I have a typed hole. I say foo is equal to underscore, and then the compiler says, well, underscore has type A to B to C. And so my brain, I now know, okay, that's going to be a lambda and 2 arguments. So I'm going to then bind 2 arguments, and then I'll put a new hole. And now Haskell says, this thing is of type C, but you have this function that returns a C given an integer. And that seems to be the only way to get a C. So it seems likely that I have to call that function. So then I will fill in that function and leave a hole for its argument. And sort of I can interactively work with the compiler to write the program. And it's a really lovely way to work. And in fact, it's the only way I write any Haskell. I don't do any real thinking about Haskell except at the level of types and algorithms. But when I'm down in the weeds writing code, the compiler and I have we have this discussion, like exactly in the same way that you and I are having a discussion right now, John, where I will do 5 seconds of work and then I will save and ask the compiler what should I do next, and it'll tell me. And so this interactive refinement process. So that's the sort of model. And Reed's realization was there's no reason that I have to be asking the compiler myself. Right? We could automate this thing where the feedback loop is just I have an idea of how I want to write the program, and so I can say, okay, Haskell, split the code, right? Like introduce the variables, now call this function, and now You figure out the rest. For the rest is just easy. So that's sort of the idea of tactic programming, and we can do this search problem where we say, I know what's in scope and I know it will type check. And so if I say call a function, we can just try it. We can just fill that hole with all of the possible functions that will satisfy or that will type check. And then on the next step, we can just have all of these in superposition and we can try to solve them. And if we succeed in ever getting rid of all the holes, we have a solution. And that code is guaranteed to type check. Not guaranteed to do the right thing, but often when you're working polymorphically enough, there is usually only one solution. So yeah, Reed was really excited about tactics. And Haskell language server had sort of just come out or just gotten to a point where it was workable and had a plugin system. So we thought, let's spend a day integrating this. How hard could it be? At the time, I was actually thinking about an alternative method of programming, which was, I was sort of jealous of mathematicians who could go and be in the park with a notebook and sit in the sun and be productive without like carrying a laptop out and trying to find Wi-Fi and that sort of thing. So I was sort of thinking about a world in which I could do programming on my tablet. And on a tablet, you don't want to be like writing code. You want to be choosing. You want to sort of be in the navigator seat, where you want to say, here's the code, and I want to give the computer tips about how it should be filling in these holes. So that was sort of what I was working on, and Reed and I realized like we were a good match for this problem. So the easiest place to do it was not to write a tablet app, but to just stick it in the language server, and then I could call it later. So that was the idea for Wingman was let's put a tactics system into the language server. And the problem with, maybe not the problem, but the tactics engine requires you to articulate what it is you want to be doing. And so at the time, we just sort of bound that to a few actions in the language server. So you had a little light bulb, you click on the light bulb, you can say fill in lambda, or you can click on it and say add a data constructor or something like that. And so what those would do, those would each run one step of like the tactic language. And we didn't have a tactics language that was user programmed. So you would just do one action at a time. That turned out to be fantastic and most of what people wanted. So someone filed a bug report or a feature request saying, can you please add case splitting? Because we could do it by introducing like a case of expression, but we couldn't split function definitions into multiple clauses. And it's actually not a hard problem. The hard problem is just splicing the text in. That's the hard part. It's ridiculous that we're in the year, I guess 2022 or whenever that was, that like syntactically modifying the program and figuring out all the clauses, like that's the easy part. And the hard part is, how do I turn it into text, right? And in particular, how do I turn it into text such that I don't disrupt everything else in the file? Where do I put it? At what indentation level? How do I not delete comments when I do that? And so I'd say like 60 to 70% of Wingman was like dealing with that kind of stupid stuff of just how do I splice some code and view it as text into this like AST, but no parser unparser problem. That was all through. There's a library by Alan Zimmerman called GHC exec print, and it dealt with some of these problems where it would keep annotations from your source code, and then just extremely loud motorcycle going by. So it would keep track of these annotations, and then you could then serialize back the AST, which has none of the syntactic pieces, and you could turn it back into a document. And that worked, except that there were no facilities for like synthesizing new code because the annotations were kept separately from the AST. So we had this problem where I could pretty print code that I already had. If I could parse it already, I could pretty print it back, and I could delete stuff from that, and that would work. But I wanted to synthesize new code, and because of that, I wouldn't have any annotations, and because it didn't have any annotations, the pretty printer or the exact printer would just ignore it, and it would not actually output anything.
Mm.
So the solution to that was like I would use the GHC pretty printer and say like, here is some syntactically valid Haskell, and I would parse that back with the exact printer, which would then give me the annotations, and then you could sort of munge them together and like pretend it's a monoid and that it had nice properties, which didn't. But so yeah, so that was it. Wingman could not have existed without Alan's work on GHC exact print. But the technique of keeping it separate was too problematic, and with the language server becoming as popular as it was, it turns out all the plugins needed to be able to do this. And so everybody was solving the same problems, and it was hard for everybody. So the GHC headquarters decided like we should probably keep these annotations. So Alan did this huge amount of work in order to push the annotations directly into the GHC representation of the Haskell AST. And I think that's the right place for them. However, it is such a breaking change that it's infeasible to fix Wingman. And I guess I've been working on it for over a year at that point. Just
Wow.
It's all open source. It's all, nobody's paying me to do it. And then you get a huge refactor like that, and it's just not a thing you can will to happen, right? If someone were paying me salary, I could probably get it done, but yeah, just I think it's a flaw in the Haskell world, which is the sort of you need to break things in order to make the language as good as it is, but when doing that, like we don't really have a migration path.
So, like the issues you face, like I kind of follow Haskell like someone who follows a sport who's not particularly great at the sport, but is a fan. So I spend too much time on Reddit and GHC mailing lists and following all the shenanigans that's going on. And like breaking changes are always, a source of entertainment on those platforms.
They are, yeah, agreed.
And I always think, if only there's a way you could like if we're going to make a change of a type to actually pass the application, pass the source code and regenerate it in the new way. And I presume that this problem you hit with Wingman would be the same for someone trying to write something to fix source code, depending on like if some sort of if there was some relatively complicated refactor that was required, trying to automate that, you'd want to be able to read these symbols and munge them around and merge them and push them back like you did with Wingman. So I presume that this is going to be, quite a problem for like it's quite a problem for a lot of people trying to do things with the. Well, yeah.
I think that it feels like it should be an easy transformation, right? It feels like it should be. But the problem is there isn't a GHC API. There is GHC internals exposed, and we pretend it's an API. And so it's not actually, it's just like whatever makes sense in GHC is what gets exposed. And that changes dramatically between versions of Haskell. So like 9.0 to 9.2, it's dramatically different often. And so if you're in the language server, you want to support multiple versions of GHC. And so now you have this piece of data that is denormalized in one version and it's normalized in a different version, and it's in completely different places on both of them. Just the mechanical headache of like, how do I reconstitute this piece of data that I need that isn't documented anywhere, that I got the first time by trial and error and saying like, oh, it seems like it's reliably in this place. That moves around, and now not only do I have to reverse engineer, I also have to figure out a shim that lets you do it between the two versions, and that turns into this mess of like C preprocessor macros and all sorts of like awful things. And that's just to get the data that you need. That's not then to then the exact print stuff is now the entire data model has changed. And not only is it like it's moved libraries, right? So it's just like such a hard problem. And I think it's something that probably will get solved at some point. I think the GHC guys do seem pretty keen on presenting an API, but nobody knows what that API should look like.
I think there's a Haskell Foundation announcement. It was Alexis King charting a course towards a stable API for GHC, but I don't think I've seen anything since. But yeah, it's I think it's one of their priorities. Yeah, because it's been.
Yeah, it sounds incredible. Yeah, Lexi will be my favorite person if she can pull it off. Yeah, I don't follow the Haskell news too closely these days. I'm just off social media, which means I'm sort of off all the places I might see it. But I will read the release notes whenever they come out, and I think I'm still running GHC 8.10 because it's the last version that supports Wingman, and I like case splitting too much. So it's a silly reason to not upgrade, but it is a real reason, right?
Absolutely. Well, I think I've pretty well done most of my questions. So I don't think, are there any, Lyndon or David, are there any questions missed in the call messages? Sorry, in the messages?
Someone was asking about how it's demand for Haskell devs.
Yeah, I don't know the answer to that. I think it's reasonably good. The hard part is getting your foot in the door, and I don't think I'm not in a position where I think it would be too hard to land a Haskell job personally. But I think there's a huge amount of people who are excited about the language and want to do it professionally, but they unfortunately don't have industry experience. And then they're competing with all these other people who don't have industry experience but would like to get some. And so on average, I think those people are probably more junior, at least maybe not as engineers, but just in terms of getting things done in Haskell. There's something about doing it professionally that seems to just hash out a lot of like design patterns and sort of things. So my understanding is there's quite a lot of jobs, but getting your foot in the door is harder than it should be. I don't really have a good solution for that other than get lucky.
Cool. So what are your current and future plans for the next 3-4 years once you finish thinking in new types?
I can't imagine planning anything further than 6 months away. I don't know how people manage that. My life is, I don't know. I get bored of things after about 6 months, and so currently I am working on a programming language at a startup. And I'm under NDA, so I can't say too much about it, unfortunately. But there are a lot of intriguing problems to be solved there. And so yeah, so right now I'm just sort of enjoying having a job. It's the first time in years that I've like had a job that like requires me to think about a problem regularly and get paid to do it. And it's a really nice means of external motivation where, writing a book is you just have to force yourself to get it done. And someone paying you helps a lot for the motivation front. So really enjoying that. I think I'm done with writing books. This last one was such a slog that I don't expect to write another one. I'm sure that'll change. I would like to spend more energy trying to figure out how do we do functional programming in the large. I think this is in the preface to one or maybe all of my books, but it seems like we're pretty good at doing functional programming. We're talking about numbers and like obviously pure things, but as soon as you want to connect to a network or like build a web app, all of a sudden we forget how to do all that stuff, and we say, oh, we'll do microservices and we'll do an actor model and they'll all have a global piece of state and we'll pretend that's fine. And then we'll worry about database migrations, and it's like, what the hell, right? I think there's a huge amount of improvement that can be made there if we sat down and thought about it and like admitted that the status quo is awful. I don't exactly know what that would look like. Something I've been toying about with for quite a while is the idea of a dependently typed database. Or at least a strongly typed database, where right now we've got SQL, right? We've got Postgres or something, and it has some primitive types like strings and numbers, but you can't put your own types in there. And if you do, you sort of have to encode them either as text or as JSON. And so now you have this like weird world in which I have to marshal to and from this thing every time, and so I have to parse it every time. So I can't actually trust anything in the database. And so all of a sudden, like there's this very clear boundary between my program and the database. So I think there's a world in which we can make like a strongly typed database where the type system in the database corresponds exactly to the algebraic data types or something. And so you can say, you can model types in your database and export them directly to Haskell or something, and then like not have to pay that marshalling and not have to, and you can just forget that there's anything there. I think that is sort of holding us back, is we across all of computing, where we don't take type seriously enough. So like on the file system is another example of this, right? Where I've got like a PNG file, which I hope is an image, but every time I want to operate with a PNG, I have to import it, and then I have to like parse that thing. And like there's libraries that do it for me, but it'd be really nice if I could just load it in as data directly. Forget all this parsing stuff. Forget the fact that like we have to store as bytes, right? This is true in memory, where actually, right, memory is just a bunch of bytes that's strung together, but we never think about it like that because these abstractions hold when we're working in memory. But for some reason, they don't hold on the file system, right? And then that's always struck me as this weird distinction that shouldn't be made but is. So I think there's a huge amount of room for just taking types more seriously across like all of computing. And if you can do that, you can get rid of so much of this pain where things are strings and we have to deal with that, right? So yeah, I imagine if I was to do a project in the near future, it would probably be along those lines.
Cool. Yeah, I think Paul's asked a question about, are you into category theory? And
to an indecent level. Haskell and category theory are completely separable. There are a lot of good ideas from category theory that have been co-opted into Haskell. Usually they don't really do justice to the idea. And this, I think, this has been a stumbling block for me, where you go and you learn the idea in Haskell and you try to reverse engineer what it is categorically, and that usually doesn't work. However, I have found learning some amount of category theory does in fact help, but it helps more on the modeling side of things, where I don't know, I'm not very good at category theory, so this is all kind of, it's on the fritz. But if you know about like the product object, right? If you know about like products and co-products, we think about those as types in Haskell, but those things correspond, those things are like everywhere in mathematics. And if you start thinking about them as like the categorical object, you start to see more things, and you start to see maybe like more relationships between things that seem otherwise disparate. And that's been helpful for me. The other thing I think is the ones I really have gotten a lot of value out of are like the recursion schemes, which I imagine have a huge amount of category theory backing, but I don't really know. It was a great paper by someone, I've forgotten, but paper called Fantastic Morphisms and Where to Find Them, and it's on all the crazy recursion schemes and the categorical semantics of them. And that sort of stuff I found is really valuable just for knowing about the pattern, where you can look at a problem and say, this problem feels like a catamorphism, and that's not a word I would probably have if I were not exposed to the category theory and to the Haskell. And so it's not that I couldn't solve the problem without it, but as soon as you have the word and the concept, it really makes tackling the problem much easier, because I know what properties it must satisfy. And once you say, this thing is a catamorphism, I can just go and pull in the library. And now I don't have to write that function. So getting a feel for the categorical ideas, I think, is more important than necessarily doing the category theory. And I'm sure that the purists will yell at me for that, but yeah, I think, in the same way we do Haskell because it's sort of fun to be this pedantic about how good our code is, I think that's how the mathematicians feel about category theory. I'm not sure it's super useful for like an everyday programmer, but I don't know. I've gotten some value out of at least pretending like I know what I'm talking about.
Cool. So, where do you see Haskell going in the next few years? Is there anything in particular that you're excited about on the horizon there?
Not off the dome. I feel like Haskell has most of the things I want out of it. Let me take a moment to think about that. Type families are kind of awful. I would like there to be a better solution than type families. I don't know what that would look like. But in terms of features I know about, I don't think there's anything I'm super excited for. The post-qualified post-qualified imports, that has been amazing change recently, where you can write the word qualified after the module name instead of before. So like dumb stuff like that is fantastic, right? But no, I don't think there's anything I'm like really looking forward to in Haskell. Maybe one thing is multiplicity polymorphism for the linear types extension, which is to say you can write some code and then Haskell will polymorphically decide if it should be linear or not. And I found that was really lacking the last time I tried to do anything with linear types. I guess actually, what I would love is some love and care put together or put into the arrows interface. Because arrows in Haskell, if you don't know, it's this extension that lets you write things that are just kind of close to monads, but it's statically verifiable. And so you sort of write this flow chart. I think flow chart is a really good idea or semantics where the flowchart itself is static, but the data that moves through it can move dynamically. And so Haskell has a notation, or has an extension and explicit notation for doing this. And it's a really, really fantastic abstraction for all sorts of data flow modeling and all sorts of things that the Haskell is a great tool to model. But the extension itself is pretty awful in that it's usually unusable for all the things we would want to do, because it just desugars really badly, and not for any deep theoretical reason. It's just that's how it happened to get implemented. So I know Lexi Lambda also has been putting some energy into that. I don't know if that's going anywhere, but personally, I think that's the biggest wart in Haskell right now, is that we have this fantastic interface and the implementation of it is quite bad right now.
Okay.
Did I ever try the Needle library? I have never tried it, but I think that's the one that parses an ASCII flowchart into an actual arrow, if I'm thinking of that correctly. Yeah. And then there was another question on Lyndon was asking about modeling quantum field theory and game theory. Did I run into any non-constructive concepts and proofs? And what did I do in that situation? Yes, often. So I guess constructivity is the idea that mathematically we don't have the axiom of choice, which is to say we can do computation on these things, and you don't have to pull something out of nowhere. And mathematics is pretty famously non-constructive, which is pretty awful. But what you can do in those situations is you just postulate that you have the thing that isn't constructive. And you say, okay, well, if this axiom were to hold, I can still model it. And that gets you through the problem. I don't try too hard to construct those things. Well, actually, that's not true. So we were working on a game theory thing where you have some probability metric, and one of the axioms, you can like sort of subdivide it and say this thing is continuous. And modeling that actually was more annoying than we wanted, because now you need rationals, and then you need to take the limit, and you need to get real numbers, and we didn't have real numbers, and modeling the real numbers did not seem like a valuable use of our time. So yeah, I think getting work done in proof assistance, usually I found what works best is you do the work you want to do. As soon as you get stuck, you postulate something, so long as you're pretty sure it's true. As soon as you postulate things, it usually goes wrong, but you try your very best and you hope, and you don't postulate anything. You think about it before you postulate it, which is the thing I learned the hard way in the book, where I got really far into modeling so what is it? Complexity theory, computational complexity theory, and like trying to prove Cook-Levin theorem. And that stuff's awful. I'm pretty sure no one's actually done it. Which is to say, like, we can encode a program, and then we can determine like the polynomial runtime of the Turing machine that evaluates it. And I've only ever seen sketches of this. Apparently it's late and I'm meandering now, but I'll tackle this anyway. So there's sort of sketches of Cook-Levin, which is to say SAT. The SAT problem is NP complete. And they do that by sort of encoding so the other way around. Yeah, so you model a Turing machine as a satisfiability problem. And I've only ever seen sketches of that. And it's sort of clear you can do it, but as soon as you actually try to do it, it's really, 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 really awful. where you sort of need to give bounds of like exactly how does my Turing tape tick and how does it move and how do I bound these things. And the book was originally going to be much more about sort of computation than it ended up being about mathematics. But I'm pretty sure like low-level computability theory is a ball of mud, and it's not actually a good foundation at all. So anyway, sorry, I'm rambling.
Cool. I think I'm done with all the questions I have, and we.
Oh. There's this question from Lyndon about parkour, which I think it might be fun to answer as well. I'll do it quickly. Yeah. Has parkour taught me anything that applies to Haskell or life in general? I don't think to Haskell, no, but to life in general, yes. And parkour is fascinating because it is not very physically challenging. And the hard part is all the mental, where I'm like pretty sure I'm not going to get hurt if I jump over this railing. And I practiced it a million times on the ground. But as soon as you're 3 stories up and you're trying to jump over the railing, even though you know you've drilled the skill, at some point you just need to overcome the mental barrier. Almost never is the problem physical; it's always mental. So, my sort of takeaway from that is that I haven't really been trying very hard in my life, right? Where the challenge is more like, it's not am I capable of it, it's like am I willing to go through the pain to do it. And it's not a pain of like the effort, it's a pain involved of like the fear and the uncertainty of, can I accomplish this? Am I willing to put myself out there and try? And that is so much harder than the actual work involved in accomplishing it. It's just the trying part. So I'm not there yet, but doing parkour has made it really, really obvious when I'm like chickening out without realizing it, or previously before where your brain's sort of making excuses for why you shouldn't do this thing. And parkour has made it really clear to me when that's happening.
Mm-hmm.
Yeah. Maybe that's a good place to leave it because I'm losing it apparently.
Well, thanks for. I mean, what time is it there? It must be what?
2:30.
2:30. Well, wow. Well, thanks for joining us, Sandy.
My distinct pleasure.
Thanks for spending the time. Your books, your libraries, your blogs. I'm sure I'm a big consumer of all 3, and I'm sure the others in the group are. So, yeah, it's been a blast having you on, and thank you.
For me as well. It's really, really lovely to be here. Thanks for organizing this, and hope everyone has a fantastic day.
Thank you. Thanks, Sandy.
Cool. Yeah. Bye.